Welcome back to the deep dive. Today we're really getting into the nuts and bolts of a crucial piece of kit, the Directional Gyro Indicator. You'll hear it called the DGI, or sometimes just the DI, the Direction Indicator.
That's right. And our goal today, especially for you tackling ATPL theory, is very focused. We're going to break down exactly what you need to know about the DGI, think principles, limitations, and critically, its errors. That's where the exam questions often lie.
So why do we even need a DGI? Well, it's all about getting a stable direction reference, something you can rely on to keep a steady heading or make precise turns, unlike, the magnetic compass sometimes.
Yeah, the compass can get pretty wild during turns or acceleration. The DGI gives you that solid, deadbeat indication. Doesn't swing around.
And this leads us straight to maybe the most important point, something you absolutely have to nail down.
It really is fundamental. The DGI has no magnetic element in it at all. Zero.
That's huge. So because it's purely mechanical, purely gyroscopic.
It's not north-seeking. It has absolutely no idea where magnetic north is on its own.
Which means you have to tell it.
Exactly. You must set it initially, synchronize it with magnetic compass, usually when you're flying straight and level, nice and steady, when the compass is behaving itself.
And it doesn't just stay there, does it?
No way. It drifts, it wanders. We'll get into why later, but because of that inevitable drift, you've got to keep checking it against the compass regularly. Think every, 15 minutes or so?
Right. So they work together. The DI gives stability. The compass gives the actual magnetic direction. They complement each other.
Precisely. They aren't substitutes. Okay, let's dig into how it actually works.
Okay, the mechanics. We hear gyroscopic rigidity thrown around a lot.
Mhm.
What's the actual setup inside that lets the DGI hold a direction? You mentioned it uses a tied gyro.
That's the term, yes, a tied gyro. It's basically a gyroscope that has freedom to move in 3 dimensions: pitch, roll, yaw, all at right angles to each other. But crucially, it's engineered, it's tied by a system, so that the spinning part, the rotor axis, is always kept in the aircraft's yawing plane.
The yawing plane. So when the aircraft's flying level, that axis is horizontal.
Exactly, perfectly horizontal in level flight. And
Like-
that spinning rotor, going at thousands of RPM, has enormous inertia, that's the rigidity. It wants to stay pointing in the same direction in space, resisting any attempt to tilt it.
Okay, so how is it mounted to allow that freedom but also keep it tied? Let's picture the components.
Right, so you've got the rotor itself spinning like crazy. That's mounted inside an inner gimbal. Think of it like a frame. That inner gimbal allows it to tilt, but its movement is restricted.
Okay.
Then that inner gimbal sits inside another frame, the outer gimbal. Now, this outer gimbal is the key part for indicating heading. It's mounted inside the instrument case on bearings, and it can spin freely, a full 360 degrees, around the aircraft's vertical axis.
So the outer gimbal is what the heading scale is attached to.
Usually, yes. The whole setup rotor axis, inner gimbal axis, outer gimbal axis, is carefully made to stay mutually at right angles.
So let's say the pilot banks the aircraft and starts a turn. The aircraft itself and the instrument case fixed to it starts rotating around that vertical axis.
Correct. The case moves, and the little marker line on the case, the lubber line, moves with it.
But the gyro?
The gyro says nope. Because of that rigidity, the rotor, the inner and outer gimbals, and the compass scale attached to the outer gimbal, they all resist that turn. They try to stay pointing exactly where they were in space, fixed in azimuth.
So the scale stays still in space, and the lubber line moves across it, showing the new heading.
That's it, and it's immediate. No lag. That's the DGI's strength right there.
Okay, but if the gyro just wants to stay fixed in space, how does the instrument make sure the rotor axis stays horizontal in the aircraft's yawing plane? Compensating for tiny nudges or imperfections, especially in those older air-driven ones you see in exams.
Good question. In those classic suction-driven gyros, the air system does double duty. It's actually quite clever. Well, first, obviously, the air jets provide the rotor drive. You've got these twin streams of air hitting little buckets cut into the edge of the rotor. That's what skins it up to, maybe 10,000 RPM or even more.
Okay, spin.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best